Okay, so last time we were about halfway through the discussion on collinearity. Are you feeling collinear today? At least a little bit linear? So we'll finish that discussion and continue on with this whole concept of model selection. Oh my gosh, dude. Don't get me. You guys have tested? No. Yeah, don't get Peyton riled up. I'm getting a new calculator tomorrow, so we can talk about it.
The Inspire, the Inspire CS.
Oh, yeah.
Oh, yeah. One. Early get.
You know, there are some schools that have banned those inspired in classes because you can cheat with them, right? You can put a whole document in there.
It's amazing,
I
yeah.
love Inspire.
Well, up to like 64 megabytes or something.
No.
Text doesn't really take that much, so.
Okay, so last time we were talking about collinearity. So remind me what that means. What does it mean to say two variables are collinear?
They're related.
Okay, they're related. They tend to, right, they have a high correlation, right?
So it would be fair to say that they are highly related to each other, not just that they are related to each other.
Right.
So if they're related to each other, but there's enough that's not that relation, they can still be viable. Those can still be viable variables.
Yes, almost always. If two different competing x variables are candidates to go into a model to predict y, there's going to be some correlation between those x variables. I mean, if they're not, it's rare that they are both related to y but not related to each other in any way, right? So there's going to be some level of collinearity, but it becomes a problem when it's too strong, because when it's too strong of a correlation, then the computer algorithm kind of starts to fall apart.
And that's where we got the cutoff, is if it's greater than 10, so you should worry, I should say.
That's right. So now remember the VIF, the discussion of VIF, which I have here in a model statement in a proc reg as an option. So I have a slash and then COLLIN for collinearity. That's an option in SAS for it to give you the collinearity diagnostics for you to look at. And then another option for the VIFs. So what does VIF stand for?
It's the variance inflation factor.
Okay, good. Variance inflation factor. And how is it computed?
Take 1 divided by 1 minus r squared, and then j variable, whatever variable you want to look at.
Okay. Now, that's kind of where I left off, right? Is we were just defining what this r sub j was. And I got the definition out, but I didn't have a chance to show you. But what does the sub j mean?
Xj is equal to, it's basically a linear function of all the x's.
Okay. So rj squared is the r squared from modeling xj equal all other x's. So that's bad notation, cryptic, but you get what I mean, right? So we're going to show that with this VO2 max data. Right, so I just loaded it into memory, and if I do the correlation matrix, then we see that, for example, lean body mass, LBM, is pretty highly related to weight. Right? So somebody's weight is dependent on their lean body mass. It's also highly correlated with their height. It's also fairly highly correlated with VO2 max, which is the y variable. None of the other variables does not seem to be related to age at all. Right? What about percent body fat? It's negatively correlated, 0.575, so it's fairly strong, not real strong correlation. It's not as strong as I would have expected. Percent body fat and lean body mass. Does it make sense they're negatively correlated? Well, you kind of have to know what lean body mass is, but it's a measure of
It's like muscle.
yeah, muscle weight, basically. What's your non-fat body weight, right? And so percent body fat, you would expect that to be negatively correlated with that. So when I run a model that has all or several of these variables in it, here is a model that has height, weight, treadmill time, lean body mass, and percent body fat. And I've asked for the variance inflation factors. Right?
How come that looks like that? Are you just not looking at the HTML version?
That's right. I turned off HTML. I finally figured out this is the old school SAS, and it's much easier to deal with when you're cutting and pasting things around. So I went with that. But it's the same stuff, just looks a little different. Okay, so now what are we supposed to look at as our cutoff for variance inflation factor? 10. So we've got 3 of them that are above 10. One of them just barely. Right? But the biggest one is 83, and that's the lean body mass one. Okay? So let's show where 83.4203 came from. Right, using this. So R squared sub LBM. Instead of a J, I'm going to use LBM. So I don't have to remember which number it is. Right? Tell me how I get that.
It would be,
1 over 1 minus 0.8592.
yeah, 1.
Okay, let's try that. 1 over 1 minus 0.8592. Give me that.
That one.
That's
That one.
one.
Right.
Yeah, it's not going to be right.
What is that?
Not right.
No.
It is not right.
It's going to be 1 divided by the VIF minus 1 equals R squared.
Yeah, but 1 over 1 minus should have been the VIF, and instead of 83, you got 7 point something. What's wrong?
You took VR squared of.
Read this.
You not model it to VX.
You got to take this LBM, make it the Y variable, and model it based on the other X variable.
I thought you did that.
All right, yeah.
No, this is the VO2 one, right? And in the VO2 as a dependent variable, then I'm looking at the variance inflation factor for LBM, right? But for me to reproduce that, I can't get it from this model. I have to run the model with LBM
You
as
could find out
the
that
Y variable.
you could find out that R squared LBM without
Okay? So look at this code. Procreg model LBM equal height, weight, treadmill time, and percent body fat. The other 4 variables. This one has 5 variables. So what you're doing is you're taking one of those variables and making it the Y variable. So VO2 max is not in this at all. Right? So it's just how much of the variability in lean body mass can be explained by correlation with the other 4 variables. That's the R squared sub J. So I'll run that. And now we get R squared of 0.9880. Now think about that number for a second. All of the variability, not all, most of the variability in lean body mass can be explained by these four variables: your height, your weight, your treadmill time, and your percent body fat. Does that make sense? 98.8% of the variability in lean body mass. So that tells me, hey, I've got some collinearity going on. Right? Lean body mass seems to be collinear with some of the others. But now we can compute this, so redo it. Instead of 0.8592, 0.9880, and what does that give?
83.33 repeated.
Okay? 83.33 repeated. Now that's not exactly what we had previously for the variance inflation factor. It was, I thought I'd written it down. It was 83.42 or something like that.
Can't we scroll up to find it?
Yeah, we can go get it. But why is it not exact?
It's just round off there.
It's just round off error. And there's a couple of things that were rounded off. So there it is, 83.42. A couple of things that were rounded off, mainly that. Right? That's been rounded off. I guess that's it. And how would I get that? If I wanted that to more decimal places, what could I do?
Just go back to squared.
Yeah, go back to the table that gives me the sums of squares and compute R square myself by taking sum square model divided by sum of squares total, and that'll give me more decimal places, which then you'd hit this. It's not worth the time to do that. Okay, so
Can you just go back down to the,
that one? Yeah. Okay.
How come you don't use the adjusted R squared, since we're dealing with more variables? Like, because if we add another one, R squared is still going to go up.
Yep, that's true. I don't have a good answer to that question. He said, why don't we use the adjusted R squared instead of R squared? And the answer is, because that's not what we do. Just historically, this is how somebody way back when they first decided, oh, variance inflation factor. I'm gonna come up with a statistic to try to estimate, how much the collinearity is a problem, and that's the way they defined it. But you could certainly do that. That's the kind of question that academic statisticians deal with all the time. Like, hey, what if I used something slightly different? Would it be better? And if it is, you write it up, you publish it. That's statistical theory.
and so now there's 4 degrees of freedom in the model because now we're just not using CO2. We used one of the models.
Right.
But it's now the Y, and so it's
Yeah, VO2 was the Y variable,
Right.
and now I'm modeling one of the 5 X variables as a function of the other 4
So
X
you're losing
variables.
one of the
Yeah.
X.
So the VO2 is not in this one at all. Right?
So if we had to do this by hand, we'd have to do this for every single one.
Exactly. You'd have to one at a time take an X variable, make it the dependent variable, and the other 4 X variables, and do all of them, and then you get those 4 VIFs or 5 VIFs. There'd be 5 of those you could do, right? Take one of these at a time out, make it the Y variable, and so you take height equal these 4, and you would come up with that 4.46, right? And so on. Now, generally what happens here is when you see 2 of them that are real big, then those are the 2 that are more correlated with each other. So lean body mass seems to be more correlated with your weight than with the other variables. So most of that 98.8% is being explained probably by the weight and not so much the other variables. Right? So now we get to the second part of the collinearity diagnostics table, and we need to discuss what these things are. And I just noticed that this output, when I took it out of HTML, I probably also have a line in here, yep, right there. That LS, you don't need to know this, but that LS option at the top is line size. and it's at 110, so it wasn't enough room for it to put the whole table, so it chopped the table in half, and it put condition index, and then below it'll be the rest. So I'm going to make that a little bit bigger, see if I can get all of them on there. Yep, there it went. Okay, I'm still going to have to scroll over a little bit, but so down at the bottom it says collinearity diagnostics. And I don't know if I can get it all shown at once. I hope I can. Make this a lot easier. Close enough. There. So it's the same stuff up here that you saw before with the VIFs. But now this table down at the bottom. What the heck is this table? Well, this is very complicated. It's a lot more statistical theory going on behind the scenes that in a class like this we don't go into. You would hit it if you go to grad school in statistics. But this column says eigenvalue.
Isn't that, we also do that in stochastic?
Linear
algebra.
Yeah, linear algebra, you'll deal with eigenvalues. That's right. And then something called the condition index, and then you have all of the terms in the model. Right? So you have an intercept term, height, weight, tread time, mean body mass, and percent body fat. Okay? So here's what you're looking at. These eigenvalues, let's start with that. Technically the eigenvalues, what's going on behind the scenes is from an area of statistics called multivariate analysis, where you have more than one y variable all being modeled at the same time. Right? So that's called multivariate analysis. And one of the techniques that's used in multivariate analysis is called principal components analysis. Right? So it's a way of taking all of your x variables and trying to see if there's linear combinations of them that help explain one of the variables on the y side, and then a different linear combination that maybe explains another of the y variables on the other side, and so on. Well, what they do is they apply that technique to the correlation matrix of all the x's and the y. All the x's plus the y. Right? So they take that correlation matrix. Then they decompose that correlation matrix into a set of linear combinations of these x variables that still explain exactly the same amount of the variability in y, but they are now uncorrelated with each other. So you take that correlation matrix and you can decompose it and say, well, this amount of the total correlation is coming from these variables, and this amount's coming from these variables, and you can fix it up so that the new variables are uncorrelated with each other. Whereas these are all correlated with each other, and lean body mass is very highly correlated with weight, we had an issue there. Right? So the way the author writes it is like this. The x's, so we'll call them xj's, where the j again is just generic subscript, so you have variable x1, x2, x3, and so on. Right? The xj's are decomposed, that's a bad word, decomposed into a new set, x star sub j.
Nice for the eigenvalue.
Yeah, this is to get to the eigenvalues. So those xj's, you think about the x matrix that has a column for every x variable. What you're going to do is you're sort of break those apart and put it back together in a special way so that all the variability in y is still explained, but these new x variables are not correlated with each other. So now I've got an x matrix that was just like the one before, only it has x stars for the columns. When I do the model, you do my x prime, x inverse matrix, and and get my beta vector, I'll get exactly the same beta vector, and I'll get exactly the same R square out of that model, but I've got different columns in the X matrix. And those columns are specially set up so that they are uncorrelated with each other. So their correlations are all 0.
So is that a way that they try to find, like, is that a way to find like other things that are going into the variables that you originally tried to use?
Yeah, and you'll hear this is done in the social sciences a lot. This kind of a principal component analysis, and they'll use the term. These variables are loading most heavily on that. So most of the variability is coming from these. You're trying to break it down into which ones are explaining which parts of the variability, right? So the xj's are all uncorrelated but retain all of the information to explain why. So you haven't thrown away anything. You just sort of rearranged it. So, then I have in my notes here, we don't need to understand how this is done. But now the variances of these new variables are called the eigenvalues. That's these eigenvalues. Okay? So now think about the variances. When I do a covariance matrix, right, which is a correlation matrix is the covariance matrix divided by the standard deviations or variances, right? When I do a covariance matrix, the diagonal will be the variances of these xj's. And those will be called the eigenvalues. Okay?
So the eigenvalues, you said they're the variance of the x stars sub j's.
Right. Yeah, let me go ahead and write it down. The eigenvalues are the variances of the new x star j's.
So you could, like, if you were to end up using them, you could manipulate them like you would variance normally, right?
Say it again?
Like, if you take the square root, you get a standard deviator. I don't know if that does that make sense what I'm asking? You can manipulate them the same as you would just normal variances.
Yeah, yeah, you sure could. Now, notice what's happening here. I've got, the first column says number. 1, 2, 3, 4, 5, 6. Right? So, I only had 5 variables in there. How come I got 6 of these xj's? Well, they count the intercept term as one of the variables. So, the intercept term is here, and then the other 5 variables. Right? So, there's 6 of them total. And they are they are ranked in order. The biggest one, next, and so on. Right? Well, these bottom 2, notice that those numbers are getting awful close to 0. If you have 0 variance in an xj, what is that telling you? It's almost constant, right? So all of the variability of the y's has already been explained. We don't need this extra variable, right? It has no variability, so it's not varying along with x.
Yeah,
Or
or
with
you know
y.
which one's like 5 or which ones are they in order from above?
Nothing is, you cannot relate number 4 here to one of these. And that's what this part of the table is saying, proportion of variation. So let's see how to read that. If I look at a particular variable like, well, let's go to lean body mass. When I look at lean body mass, this is the proportion of variation in lean body mass that went in to each of the new variables, each of the 6 new variables. Almost all of lean body mass went into number 6. 99% of it, with almost nothing left. So each column adds to 1. Right? Now, where you know you have a problem is when more than one variable is putting most of itself into the same variable. So on a row, you look for values that are typically, well, they say if 2 or more are above 0.5, that can be a problem. But really, 0.8 is where I start to worry. If 2 or more are above 0.8 on the same row, then you've got an issue. And clearly, I've got a 0.83 for percent body fat. I've got a 0.99 and a 0.96.
What is your issue? Like, what do you mean by you have an issue?
What it's saying is that weight and lean body mass are, and percent body fat, are all putting most of their variability is being put into this 6x star variable.
Which is not actually doing anything for the model.
Right, or it's not so much that's the worry, it's just that they're going on to the same one, which means they're explaining the same variability in Y.
So is that why
So they are-
body mass is kind of irrelevant?
And that's why lean body mass has such a high variance inflation factor, because it's loading almost all onto a variable with no variance.
Yeah, at the same time weight is doing the same thing.
So these other two column, or this column, condition index, the condition index is, let's see, I don't need this anymore. The condition index is a way to just kind of like the variance inflation factor, give you one number that you can look at and go, oh, look, there's a problem, or no, everything looks okay, right? The condition index, if it gets above 30, then you've got trouble. And we've got some that are way above 30. So the condition index, which I'll call CI, condition index is the square root of lambda 1 over lambda j. And this is condition index for the jth one. And jth being that number, the left number. So lambda 1 is the eigenvalue that's at the top. So it's the biggest one. Right? So if the biggest eigenvalue divided by the current eigenvalue, j, and then you take the square root of that, if that ratio is too big, then that's saying, hey, you've got an issue here. Right? And so it's a way of detecting when these things get too small, too close to 0. So I've always thought, well, wouldn't it be easier if you just give me some kind of cutoff for when these get too close to 0, rather than having to flip it and do a reciprocal thing? But it has to be relative to how big the biggest one is. Right? So the biggest one is lambda 1. Then the largest of these, since these are put in order, the biggest one down here at the bottom is always the max, right? I mean, it'll always be sorted so the biggest condition index is at the bottom. So that biggest one they call the condition number. Right, so condition number. If Cn greater than or equal to 30, then collinearity is a potential problem. If you Google this collinearity thing and do a lot of studying on your own about regression modeling, you'll find that there's some controversy out there. Some people say, oh, you don't have to worry about it unless it's above 100 or whatever. And sometimes, like this one, it seems to be pretty extreme. We're supposed to worry if this is above 10, and that's way above 10. We're supposed to worry if this is above 30, and that's way above 30. But yet, if you look at the model seems to have done okay. There aren't any standard errors that are way out of whack, or you know, parameter estimates that seem to be blowing up to infinity or anything like that. So, yeah.
But couldn't that all depend on the type of statistics you're working with? Like it's like pharmaceutical stuff, it probably needs to be more in check than.
Well, yeah, it has to do with the kind of research that you're doing. That's for sure, and that's often the case. Is that some areas of research accept more of you know, weird things happening than others do, and will tend to lead to more of this kind of thing. But here, it has more to do with the measurement scales on the things that you're measuring, as to whether these things become a problem. Even when the condition index gets big, it still might not be a problem if the scale of measurement is okay and the numbers aren't causing a problem internally in the computer.
That's what I'm saying. Like if you're doing like estimating election outcomes compared to like how a drug is going to affect a human being, child or something.
Yeah.
I'm sure there's different standards.
Yeah, that's very true. Different standards. So, to assess collinearity, you use both the variance inflation factor and then this whole bottom part of the table, starting with looking at condition index and saying, "Ooh, look, I got one or more of these that's bigger than 30, so I need to assess it." It's not necessarily saying the model is no good. It's to say I need to assess it. It looks like I've got a problem here. So now I start looking into here to see what the problem is. And I see, oh, you know what, the biggest one I got is here, so that's matching the biggest one up there, so something's wrong with lean body mass. It seems to be highly correlated with weight, because this is also very big. It's also fairly high with percent body fat, only not, it's barely above my 0.8 thing, cutoff that I used. I forgot a minute ago to look at the rows above that, but all of the other rows above that, what do you notice? Look at this one. 0.937, 0.9195, and then all the rest are okay. And this is the intercept. When something's collinear with the intercept, what is that saying? That variable height, at least in this data, is fairly constant. That there's not much variability in the heights of these people that they were measuring. Right? So, that, if you're collinear with the intercept, and I'll talk more about this on another day, but if you're collinear with the intercept, you can get rid of that problem. Right? You do what's called mean centering the data. Right? You take each of your x variables and take the mean height off of everybody's height. So then now the variable isn't what your height is, it's how far off are you from the mean. Right? You're 2 inches above the mean, you're 2 inches below the mean, or whatever. Right? So if you mean center it, then that takes, and then you fit the model with no intercept, that takes intercept out, so you've gotten rid of that collinearity problem. But you get exactly the same prediction model. Right? Or you'll get exactly the same predicted values from that model. Right? It won't have an intercept term, but all these will be mean centered. So that one's easy to deal with. But the others, so that one, no problem. I don't worry about height being collinear with the intercept. The next row up, I've got a 0.61 and nothing else big. Right? So 61% of treadmill time variability is being loaded into the fourth new variable. Nothing else is loading heavy into that, so no worries there. Next row up, everything's good, everything's good. Nothing above that is a problem. Right? So what would the strategy be? If you decide, oh look, I've got collinearity going on, and I'm not trusting my model too much because of it. Right? Here I don't really see anything that leads me to worry about the model too much, because I don't see numeric problems. Remember when I artificially made one get really collinear? What happened to the parameter estimates and the standard errors? They blew up, right? They got huge. And So I don't see that happening here, so I'm not too concerned about this particular model. It seems like, well, it's still, the computer is handling it okay. But one of the things I keep reminding myself is, you know, we were kind of joking a minute ago about VIF. Why isn't this and not the adjusted R-square? Whatever. It's because whoever published the paper, whoever thought of it, right, and developed this thing. Well, think about when a lot of that was done. How powerful were computers? And you had a lot more problems with this than you do nowadays. Nowadays, they probably keep, you know, several hundred decimal places of accuracy as they're going along, whereas before the computers would round to 16, or if you wanted to double that, you could tell it keep 32 places, right? But now it can keep, it's always multiples or powers of 2, but you can keep many, many, many more than that, and the computer can handle it just fine. So it's not always the problem that it used to be. So I treat these as guidelines. I still want to look at it, but then if I see a problem, then I go back and decide, did it seem to cause a problem with the model? And a way to check that is take the one that seems to be the biggest problem, take it out of the model, and look at how things change.
So is this how you get it down to simplify your model? Like when you,
Uh,
so let's say they only want like 3 predictors and...
Yeah, it's one of the steps to pick which variables go in the model. One of the first things that you check is how well does each one by itself help predict what. So those are my candidate variables. But as we said, variables that by itself might not explain why, when you control for something else, now all of a sudden it turns up to be important. So you can't eliminate that, but then you say, oh, well, now I've got 2 of them that are highly collinear, so I don't need both of those. So now I can simplify my model by getting rid of one of them. Right? So let's look at, and write down over here, these parameter estimates. So I'm just going to write them down. -4 I'll keep just 1 decimal place of accuracy, or 1 significant digit. How about that? -0.008, 0.187 being 8, 0.057, 0.017. Right? So that's the model that has lean body mass in it. Now let's run a model without lean body mass. See if these things change dramatically.
Is there a
Like
reason why you
dramatically.
picked lean body mass again?
Or did you just?
Because it seems to be the worst offender.
variance inflation and the...
Right,
Yeah.
okay.
Okay? Now, if lean body mass, and I didn't remember to check this, but if lean body mass is the most highly correlated with the VO2 variable, then I might not want to be throwing it away. So you might say, well, what does it seem to be collinear with? Let's get rid of that. But, so,
But everything is significant except for triangle time.
right. So let's go back to the correlation matrix. This is the bottom line of it on this page. So this is my Y variable, VO2 max, and lean body mass correlates at 0.83, and it is the highest of all of them. So I might not want to be throwing that variable away. Maybe it's one of the ones it's collinear with that I'd be better off to throw away, right? But it's an art form. It's not, there's no set algorithm that you use to do this stuff. So we'll start by throwing away lean body mass. And what I'm going to do is I'm going to just drag it out of there and run a model without it. What do you think? First of all, check for collinearity.
Well, now your bottom one you have, you still have.
Your height and your intercept.
height.
I've got height and intercept still being collinear, but that's again, we don't seem to have much variability in height among these test subjects. That one is not so much a worry, but a 63 and a 97, that's a little bit of a worry according to the book, but I wouldn't worry too much about it. Look at my variance inflation factors. None of them are above 10. Condition index, wow, still a 103, but that's because of this intercept thing, right? Question?
Not necessarily a question, but more of an observation. the R squared has practically not changed at all.
Right.
Good, I'm glad you saw it. So this R squared is 0.8541. What was it with lean body mass in there?
0.85 something.
I think it was 4.0.
40. So it changed at the 4th decimal place only, and only by 1. So this model is explaining virtually the same exact amount of variability in VO2 max as the model that had lean body mass in it. Right? Now let's look at the parameter estimates. Intercept is about the same. This one is about the same. This one is quite a bit different. Right? The weight variable now is, it went from being negative to being positive.
Is that because it was highly correlated with the height?
It was highly correlated with lean body mass was the weight. Right? So when I took lean body mass out, now weight is trying to explain everything that it did before, but plus everything lean body mass was explaining before. So now it becomes a positive. Do you expect a positive parameter estimate for that variable? But what is VO2 max? Have we even talked about this?
Well,
It's not an oxygen
usually
that you
when
can-
you lose weight, your VO2 max goes up by default.
That's right. Usually, your VO2 max would be negatively correlated with weight.
Because your VO2 max is the amount of oxygen your lungs can
It's how much they can process,
process.
right? So VO2 max is, does anybody know the units on it? See, this is a buddy of mine from Emporia State when we were running track together, and he was a distance runner. Well, he went into, he got his PhD in exercise physiology, and he's now at Cal Lutheran, and this was his data. I collected data on these masters athletes, right? And he wanted me to help him analyze it. And so I don't remember the units on VO2 max, but basically they hook you up to on a treadmill. They put you on a treadmill and they put this mask on you, and they collect all the air that you exhale.
Isn't it
Exhale, right?
Isn't it like cubic inches?
Yeah, it has a volume thing.
It's either liters or cubic inches.
Yeah. So basically, how much of the oxygen that's going in, how much of it comes back out, and the less that comes back out, then the better, right? So you're using all the oxygen, and so it's a measure of how well you use the oxygen that goes in. So if you're more well trained as an athlete, your VO2 max will go up.
Apparently it can be liters per minute or milliliters per minute.
Okay. Google. Isn't that great? All right.
It works.
So liters per minute. So it's the volume of oxygen per liter per minute or something. And so that's a little bit troubling to me that when I took lean body mass out, something that I would expect to be negatively correlated with lean body mass flipped to a positive correlation.
It's weird.
You know, so that tells me, that's something weird with that model. Maybe I need to play with some other combinations. What about treadmill time? It stayed about the same, right?
So is it because the lean body mass, you would expect the more lean body mass you have, like it overpowers the negative? Does that make sense? Like it's overpowering the weight's negative value?
Yeah, I think what's going on is that lean body mass is basically the weight of the muscle in your body, right? And so as lean body mass goes up, so does your weight. But also as your fat goes up, so does your weight, right? So now the weight variable is trying to take on two components, fat and lean, all in one, so it messed with it, right? Question?
But wouldn't you think treadmill time would be a negative value too?
Well, you have to know what that variable is. So what is treadmill time?
How long?
It's how long you can go at a set rate. You're running on a
I
treadmill
don't know if
at a
it's
certain
set
pace.
distance or-
No, it's a time. So how long can you go before you just
Okay. Never
fall
mind.
over? Start to say fall over dead,
That
but they
makes
probably
more
don't take it quite that far. But
It
right,
can happen. So the safety waivers,
right, exactly.
insurance waivers say.
Yeah. So treadmill time, it makes sense to me that it's positively correlated because the better your VO2 max, the longer you can go before you get exhausted. Right? So that makes sense. percent body fat is negatively correlated? Makes sense. As your percent body fat goes up, then you're probably not in as good a shape, so your VO2 max would come down. Notice what happened to that one. Wait, I gotta remember which order we were in. I didn't write down which.
The .57 was lean body.
So this was lean body mass. I better write that down. So this was lean body mass. So this one was percent body fat. And it's the same number, but it's flipped sign, right? So that bothers me again. This is negatively correlated, which we said we would expect. When I have lean body mass in there, then it flips sign to one that I wouldn't expect. So it's telling me that, yeah, you do have some issues with collinearity here. Things are making unexpected things happen to the model, right? So, what would you suggest we do? We're not real happy with this model either.
Would you take out weight and put back in?
Exactly. That's what I would do next. If I was the analyst working on this data, I'd say, hey, that model I don't like real well, so let's put lean body mass back in. Let's see what happens when we take weight out. Because weight and lean body mass seem to be the two main offenders. But percent body fat, remember, was also involved. So variance inflations are all okay. I still got height and intercept being an issue, but nothing else that looks very troubling. So now,
body fat still positive.
okay, percent body fat is now positive again. It went back to being positive. And that's probably due to the negative correlation with lean body mass.
But
Right.
it's pretty small. Could you just drop it all together? Percent body fat.
It's not even, doesn't the p-values even say it's significant?
Okay, good. I hadn't even looked at that, but that's the next thing you would do. It's really outside of this discussion about collinearity, but it is definitely the whole model building process. Percent body fat's doing something I wouldn't expect it to do, but wait, it's not really explaining anything necessary anyway. So maybe let's just get rid of it. And it was a partial offender on that first one with lean body mass. Remember, it was a 0.83 down here. So weight, lean body mass, and percent body fat were kind of all tied together. So maybe we only need one of the three and not two of the three.
Really, I mean, lean
Yeah, the
body
R-squared
mass
went up
percent
now,
body
Yeah, the R squared did go up. So I got a better model now with lean body mass instead of weight. Right? Which, if you think back to the original correlation matrix, lean body mass was the one that was more highly correlated, so I kind of expect to see that happen. It's not a huge amount higher. What was it before? I already forgot.
484.
854 something?
No, 8440 or 41.
Oh, so okay. So that's fair. It's almost 2% higher. Okay, so let's try the one more thing. Let's take percent body fat out also. And run this. So my R squared went from 8590 to 8568 when I took percent body fat out. That's not a significant change. I'd say, yeah, definitely I don't need it in there. Now does everything look like I would expect? There actually is a positive correlation with height and VO2 max, just because taller people have more lung capacity, right? So they have more cells that process. I always felt kind of cheated there. Then positive correlation with treadmill time and positive correlation with lean body mass. Values, did they change a lot? This was height before, right? So intercept's about the same, height's about the same, treadmill time is about the same. So These are all about what they were before. I got rid of the ones that were oscillating negative and positive and kind of acting weird. And it turns out we don't really need them. So I would settle on this and say,
The height p-value's slightly significant.
right, the height p-value is 0.0599. So it's not statistically significant at the 0.05 level, but I would probably leave it in there because that's getting darn close. There is no magic cutoff of 0.05. It's always, remember what it means. It's the probability of getting this kind of a relationship if there really is no relationship in the whole population. And it's still pretty low. It's a 6% chance of that instead of a 5% chance of that. Yeah, I'd probably leave it in there.
Is that also because you know there is that relationship too? Because this data is
yeah.
probably going to be in a short, it's not going to have, 4'5" people and 7'10" people doing it.
Yeah. Yeah, and that's an excellent point, just in real general sense of what you just said. A lot of it, I keep saying, model building is an art form, and you don't look only at the numbers, only at the statistics. You also think, well, yeah, but I know there's a correlation with height, so I really ought to control for it. It ought to be in my model. It's going to take some of the variability out of the error term. If I can take variability out of the error term, then I make all the tests more powerful because I've made the denominator smaller. Right? So the F values and the T values get more significant. So I have more power to detect things that are going on if I explain variability that I know should be explained by that variable. And sometimes you'll go through this whole model building exercise and you give the same exercise to 3 different statisticians, and guess what? You get 3 different models, right? And any one model is probably just as good as any other model, really. If you're trying to make predictions, you get roughly the same predictions. So then you just choose based on, well, which one makes the most sense? Which one is easiest to explain? Which one uses the variables I would have expected or the variables that I think should be important? Right? If one of the models doesn't have a variable that the other scientists on the project or the other economists or whatever that are on the project, the non-statisticians, they say, oh, this is a variable we know, and if you're not using it, they're not going to like your model. Right? So if you get a model that has it in there and it's just as good a model, then I would go with that. Economists are better than accountants?
I didn't say that, but I really did say that.
Well, you know what a statistician is, right? It's somebody who's good with numbers, but they lack the personality to be an accountant.
You mean somebody who can't make up math? Save you money on your taxes?
That's supposed to be funny. You guys look at me like, I don't get it. But accountants have a reputation for being boring, dull, shy people, and statisticians are even worse.
Do you know what the difference between an introverted actuary and an extroverted actuary is?
No, what's the difference?
An introverted actuary stares at his shoes when he's talking to you. An extroverted actuary looks at your shoes when he's talking to
I like that.
I say that at work sometimes.
Tina, I hope you could hear that joke. Extroverted and introverted actuaries. Ask Peyton if you didn't. Okay, so let's see. I got about 20 minutes left. I need to get to the next topic. Here it is. So now let's talk about after we've kind of decided, okay, we've got variables, we've gotten rid of any that we think are collinear or whatever, but because I need more variables, I'm going to use this same data, but we're going to go through the automatic selection routines that are built into SAS or other software for deciding which model is the best. So if you think about a model, here I have, if I go back to the full set, I've got 1, 2, 3, 4, 5, 6, 7 variables that are candidates to predict VO2 max. Right? Right? So I need to select a model that uses a subset of those 7. Well, all possible subsets, how many would that be?
7 factorial. Right?
7 to the,
I think
7.
7 to the power.
What was the question?
I think it's 7 factorial, but I'm not absolutely sure. But how many different models could you form out of these 7 variables?
7.
You could have 7 models that have 1 variable in them. Then you have 7 choose 2 that have 2 variables in them. And then you have 7 choose 3 that have 3 variables, and so on. Right? You add all that up. I think it does turn out to be 7 factorial. But not sure about it. No, it might be. No, it wouldn't be 7.
I'll do it.
Because 7 factorial says you got to use all 7, but you're rearranging the orders. So that's
Not necessarily all.
But anyway, here's the answer. Here's the only answer you need to know. How many of them are there? A bunch. There's a bunch of them. Right? So what we tend to limit ourselves to are, let's look at all of the 1 variable models. Now let's look at all the 2 variable models and all the 3 variable models. And we'll pick the best from those. And then we use those as our candidate models. Right? So we go through this process of narrowing down the vast number of possible models into ones that are true candidates, right? That are decent models. Right? So, let me. My notes, I think, are in a different order than what he has in the book. So let me. Let me see. No, it is the same as in the book. So he talks about some other criteria that are used. If I go strictly on R squared, and they call it model selection criteria. If I use R squared as my criteria, what model will it select? And by that I mean, I want the model with the highest R squared.
With all of them.
It would have the model that has all the variables in it. Right? And we've already talked about that. So now if I was going to use R squared, I would want to get a model that has a high R squared, but it doesn't get significantly higher after you start adding any more variables in. Right? And you can do that with partial f-test. Right? Because a partial f-test, remember, is a test for how much did the R squared go up when you added this new variable in, or this new group of variables in. Right? So you have 7 variables, and you notice that after the first 4 go in, my R squared never got much better than that. It got a little bit better, but not much. So you could do a partial f-test on the remaining 3 to see if the increase in R squared is significant. Right? So that's one way of doing model selection, just using R squared. But adjusted R squared is better because it won't always go up. So you could use adjusted R squared, but it'll tend to overfit the model too. So in practice, it tends to put more variables in there than you really need also. So there's one called Mallow's CP that is very popular. And the Mallows is the guy's name that first published it. And he didn't call it Mallow's CP, he called it CP. And then it got, the nomenclature, people put the name on it because that's who published the paper. So, oh, that's Mallow's thing. Yeah, Mallow's CP. So what it is, it's a way, it's closely linked to R squared, but it also penalizes you a little bit for putting too many variables in the model. Right? So it'll go up and it will peak, or actually you want small values of CP. So it'll come down, it'll peak, but then it'll start to go back up. And where it bottoms out, that's the model that CP would say is the best model. So our book doesn't call it CP, it calls it the C statistic, just a C. But then he says in parentheses, some books refer to this as CP. And that's the way I've always seen it, and that's the way SAS calls it. So we'll call it CP. But it's equal to the sum of squared error over SP squared minus and then in brackets n minus 2 times k plus 1. Okay, so let's talk about what these letters mean. The P is the number of potential variables. So it's your total number of x variables that you're considering. So for this problem, it's 7. Right, so P would be a 7. So SP squared is the mean squared error from the full model, meaning the model with all P. From model with all P variables. So SSE doesn't have a subscript, is from the current candidate model, the one you're considering.
That's what you say, the root MSE?
No, because it's got a square on it.
Oh, okay.
So it's not a standard error, it's a variance.
Got it.
Okay? So we want CP to be small. And so then the next question you should ask is, well, how small is small? And there are guidelines for that. And basically what Mallows showed in his paper was that it will tend to bottom out slightly below when it gets down to k plus 1. And I didn't say what k was yet, did I? So k is the number of variables in the current model, right? Current candidate model with k variables. So I'm going to erase my period here, put a comma with k variables, right? So the model you're considering has k variables in it out of the p. So you get k variables out of p total potential variables. Right, now, if CP is at or below k plus 1, then you've got a model that is potentially pretty good. And then you just pick the one that has the lowest value. If none of the models ever get down to that level, then you're saying, you're not going to get a very good model here, even if you use all the variables. It's just, you're not getting a very high R-squared. Yep.
Just to answer your question, it's not 7 factorial, it's 7 choose 1 times 7 choose 2, 7 choose 7, that's like 26 million.
26 million. Wow. That's more than I have time to look at. So, let's demonstrate this CP and see how to get SAS to give it to
You have
us.
7 variables, or you can have, you have 7 variables, and then you do 7 models with one variable, and 7
Yeah.
models, that's 2 variables.
I understand.
It's 7.
It's that many
Yeah.
with 7 variables?
So it gets big fast. So what I'm going to do is I'm going to go back to the model here. I'm going to add all 7 of them in here. And then I'm going to take off the collinearity options and put in model selection options. Okay? Everybody follow me? So this is just SAS code. This is my list of all the variables, so I'll just use all of this, copy it. 1, 2, 3, 4, 5, 6, 7. And drop those in here. Oops. Okay, see what I did? So I have my model with all 7 variables, but then I have a slash for an option and tell SAS selection equal R squared. And remember, R squared, that wasn't the best one. What I want is, I want to look at all possible subsets and then look at this mallow CP. But it will give me, I think it gives me the CP automatically here, but you can tell it what statistics you want printed out in this output. And I may have to look that up, but let's see what we get when we run this. Oh, all we got was R squared. So I have to list them, but now SAS will stop listing models after so many, and you can control that. And somewhere in my notes I say how to do that. Let's see. Oh, I'm sorry. I have all this. I wasn't using the VO2 max data when I was preparing this last night, and it was while the Royals game was going on. So I have all the comments that was explaining the SAS code in a different program. So model selection methods example. That's what I want. Okay, so this is the soil evaporation data. So let me load that data. Check my log window. 46 observations. Okay. Then if I run all of these variables, just drop them all into here. Now I hit an enter there just because that line got so long. But remember, SAS doesn't care about spaces. It cares about semicolons. So I have model y equal, and I've got 11 different variables. And then a slash to tell it option, selection equal R squared, but then I've listed the statistics I want it to give me. Right? So give me R squared, give me MSE, SSE, CP, AIC, and then best equals 6. And this best equals 6 is a command that says, after you print the best 6 models in each block, I don't need to see the rest. Right? Because we don't need to see all however many million this would be. Right? So let me run that. Actually, you know what I'm going to do? I'm going to go back to, I'm going to copy this code and go back to VO2 max since we've already started that discussion. I don't want to have to explain the new variables to you. Okay, so here we go. We've got the VO2 max data. We've got 100 observations were used, because there were a few missing values, and then it has the top 6 out of each of the possible models. Right? So it's giving me R squared, CP, AIC, which I haven't taught you yet, and I probably won't get to that today. But MSE and SSE, you know. So the best 1 variable model is lean body mass. The best 2 variable model in terms of R squared is LBM and treadmill time, and so on. Everybody see what you're looking at? Now look at the mallow CP. What model is best? Here's a 4 variable model, but I got to scroll down to see a 5 variable, 6 variable, and a 7 variable model. But 2.8 is looking pretty good, right? Because that's well below k plus 1. Right? K plus 1 would be a 5, right? Because I got 4 variables in that model. And so it's well below 5. Let me scroll down, and there's 5 variable and the best 6 variable model. And then the 7 variable model is called the full model, right there. And it has a CP of 8. Now, the full variable model, by definition of how this is computed, the full variable model will always be k plus 1. Right? So basically it's saying if you don't get less than k plus 1 for your CP, you're not doing better than the full model. Right? The others can get bigger than that. So let's go compute that 2.8 by hand, and that's about all the time that we're going to have. So I guess I got to see the 7 variable model to get the numbers that we need. We need, from this formula, I need SP squared from the full model. So what is SP squared? Yeah, that's the mean squared error. So SP squared is the mean squared error from the model with all P. So I've got, on the bottom of the fraction, I've got 0.12, what did you say, 68? 680. And then on the top, I need the sum of squared error from what? From the model that you're interested in. So I'll page back up. And that was the 4 variable model right here. And the sum of squared error was 11.76831. 11.76831. Okay? And then from that, we subtract off n, which was 100, minus 2 times k plus 1, and that'd be 4 plus 1. Can you see that, Caitlin, when I get? Got it? So now do this on your calculator. You should get 2.8088.
2.81.
You got 2.81? Close enough. Now the reason it's not matching exactly is we've got some round off in here. But. Okay? So the best model by Mallow's CP would be the 4 variable model that has age, that's interesting, age, height, lean body mass, and treadmill time. Now we hadn't even looked at a model with age because age was not correlated very well, right? But it may be very, very strongly correlated with some of the other variables, even some of the other variables that got left out that were fairly highly correlated with Y. Age may have kind of incorporated everything that they could do. Well, your percent body fat goes up as you get older, and whatever.
So the AIC, you want the one that's the most negative, lowest number?
Lowest number. That's right.
Is it?
Oh, for AIC,
Yeah.
yeah, it's the lowest value. And it won't always be negative, but so we'll talk about AIC next time. All right, we will see you, I guess, Monday. So have a good weekend.
Someone left their nice calculator.
Uh-oh.
I got
It'd be one of my students.
he was.